we're going to shift gears a little bit. We're going to talk about the concept of resonance. And resonance is the idea that things kind of have a frequency that they like to vibrate at or move at. So if you ever go on a playground, you're on the swing. You know that you need to push the swing at a certain frequency. You have to have a certain timing. If you can get that timing exactly right, you can push your friend way high up in the air. If you have that timing not quite so right, your friend gets mad at you. Okay? We talked a little bit about tuning forks. The pitch of the tuning fork is proportional to its length, or it is related to its length. So if you have a different size tuning fork, you're going to get a different pitch out of it. Also, maybe you've seen this on TV, you can play these wine glasses. If you have a wine glass and you fill it up with a certain amount of water, and then you rub along the rim, it'll play a certain tone. If you've got a different amount of water in the wine glass, it'll play a different tone. So what we're going to look at next is the relationship between the size of objects and their frequencies.
So what I want to show you is that things have a resonant frequency. Things have a frequency that they want to oscillate at, they want to vibrate at. Just like the tuning forks, everything does. If somebody's in the other room and they drop something, somebody's in the kitchen and they drop something, oftentimes you can tell what it is just from hearing it drop, right? You know it's a dish, or you know it's a fork, or something like that. So let's play that little game. Let's see if you can hear. I'll just set this down with me. Let's see if you can hear what I'm dropping, and maybe you can tell something about it. Okay, so unfortunately there's carpet up here, so I'm going to sort of have to wing it. Okay, I've got an object. Are you listening? Here it goes. Okay. Meter stick, pretty good. A lot of you got that. Let's try something else. Right, so you're getting the hang of this, right? You knew the first one was wood and it was long and thin, right? A lot of people said stick, ruler. You knew the second one was metal. You probably knew it was long and thin. Let's try this one. How many of you kids work on your own car? A lot of you work on your own car? Then you recognize that sound probably. That was a wrench, right? And even if you didn't recognize it exactly, you probably knew it was metal and it was clunky and big, not a thin rod, right? So things have a frequency that they want to oscillate at. So what we want to show you now, what we've been saying up to this point was that vibration causes sound, right? Vibration causes sound. And what I want to show you now is that sound can cause vibration. So I'm going to play a tune here. This is a tuning fork. Okay? And this one should be pretty much identical. Okay, pretty much the same frequency. Hopefully it's the same. And what I'm going to do, I'm going to start this one going, and then I'm going to stop it, and let's see if we can hear this. Maybe I'll set this over here. Okay. Okay, so what happened was this one started playing, and just like a person sitting on a swing, little pushes came along at just the right interval to cause it to start vibrating. If they're off a little bit, it's not going to get this thing to vibrate. But if they're at just the right interval, those little pushes from the sound waves hitting it are going to cause it to vibrate. Let's try it again. Let's see if I can get it to go back. Ooh. Okay. Now I'm going to change the frequency a little bit. So this is what it sounds like now. And I'm going to put a little weight there. And I've changed it by about, I don't know, 9 or 10 hertz. So it's a little off. It's not quite exactly the same. Now we'll go, oops. Nothing. Doesn't work. It's not pushing at just the right interval. It's like pushing somebody at the wrong interval on a swing. Sometimes you push, they make it go faster, sometimes slower. You have to push at just the right interval. And so what we're going to do now is push on this wine glass with some sound waves and see if we can make it vibrate.
So what we just saw over here was Frank could put that tuning fork at just the right frequency and excite the other tuning fork. What we've done here is we've got a wine glass, and what we're going to do is we're going to send sound into that wine glass, and we're going to see if we can vibrate the wine glass at just the right frequency. And if we can do that, well, I can already see it. We can make those little pieces of paper on the top dance, because now the wine glass is vibrating at the exact right frequency. Then Frank is just going to crank up the power, and then I'm just going to put my hands over my ears. That's cheating, Frank.
Let me try again.
Yeah, and you need to reset your detectors. They got to go on the rim. So he's watching for the papers on the top to start dancing around, like right there. He's going to... We're going to go to our backup wine glass.
You want to tell them that we ping the wine glass first?
So one of the things we do back in our lab is we actually go and we tap on the wine glass with a microphone, and we try and actually look at the frequency with that. Okay, I can see him dancing a little bit.
Try it.
Okay.
Plug your ears.
Oh, came all the way to Modesto and he couldn't break the wine glass.
Luckily, we have it on video.
So we do have it on video. So I have to go back to the screen. Frank, do I just hit play on this? How do I do this?
Click on it. Move the little... Yeah, there you go.
So that's in slow motion. You can see it vibrating. Then Frank will crank up the sound on this one. Then boom. And what I love about this is you can even see the shards vibrating as it's flying apart. Now, kind of the standing joke is that we teach physics, and we're not actually allowed to call it a physics class until we show you this video. This is the Tacoma Narrows Bridge, and this was, I think, 1939 or 1940, right before World War II. And this was a phenomenon that was related to resonance. It's called flutter. And the wind went by at just the right frequency and set up waves in the bridge, and it was actually able to collapse the bridge. And after this, they decide anytime you're going to build a bridge, you build a model first and you put it in a wind tunnel. Okay?
So the wine glass is interesting because when you see that slow motion video, you think a wine glass is pretty rigid, right? But when you see that slow motion video, you see how much it flexes, and that means it's really hard to break. I'm just trying to make an excuse now. It's really hard to break. You have to be just right on the frequency. If you're off by 0.2 of a hertz, it's not going to break. So we talked about resonance. We talked about someone on a swing. We talked about the fact that objects have a frequency they want to oscillate at. I'm told that soldiers, when they march over a bridge, when you march, right, your feet are all coming down at the same time. Boom, boom, boom. And because they're all coming down at the same time, if that frequency that they're marching happens to match the resonant frequency in the bridge, they might induce vibrations in the bridge. So they don't march over a bridge. They walk so that everybody's feet are coming down at different times and you don't get that same rhythm going. And that's how most of our musical instruments work, with resonant cavities that enable sounds to resonate. We enjoy that. We talked about the range of human hearing, and that as you get older, you lose the ability to hear high frequency. I am told that there are ringtones you can download for your phone that you can hear, but your parents can't. Yeah. You never know when your knowledge of physics will come in handy. But don't worry, we'll get even with you. There are some store owners that don't like the teenagers hanging out in front of their store riding skateboards, so they put speakers up and they blast high frequency out there, drive them away. We talked about how we make sounds and the speed of sound, and please take good care of your hearing. It never gets any better. Please take good care of your ears. The physics of sound all around us. So we're going to talk about our last topic, pressure, and the first thing we're going to talk about is atmospheric pressure. Atmospheric pressure is caused by the weight of all the air in the atmosphere being pulled down and weighing down on us by gravity. All the air in the atmosphere pushing down on us because of gravity. Can you feel it? No, you can't feel it, can you? Because it's pushing on all sides of us. But fun things happen when you can remove atmospheric pressure from one side of an object or add extra pressure to another side of the object. And Brian's going to show us a couple right now.
Now, what I have over here is a flask with a little blue balloon inside of it. Now, this blue balloon has a little bit of air in it, and that air is pushing on the insides of the balloon, trying to make it bigger. But because there's atmospheric pressure in this flask, because there's air in there, the air is constraining the balloon so that it can't grow bigger. So what I'm going to do is I'm going to give this flask to Frank, and he's going to remove the air from inside. Now watch what happens when Frank runs his vacuum pump. As you can see, once we remove the air, the atmospheric pressure from the outside of the balloon, the air from the inside of the balloon is effectively allowed to push outwards and expand. And now, when Frank removes our vacuum pump, the air will rush back into our flask, and the balloon will shrink back to its original size. Now what we have over here is just your ordinary average lab stool. It's completely ordinary, and atmospheric pressure is pushing in on all sides of the stool. The top, the bottom, the sides, every possible surface you can see, air is pushing on it, this stool. So what I have over here is a little mat, and I'm just going to slide it over our stool. And between our mat and our stool, there's a little vacuum. So effectively, no atmospheric pressure is pushing on the top of the stool. So what I can do is I can grab our little mat like so, and voila. Even though our mat isn't sticky at all, it's able to lift our stool up using just the force of a vacuum. Now these are two metallic plates. If you look really closely, you can see a little cavity right here. Now, what do you think is going to happen when I put these two plates together like this? Not much, right? There's still air in between, so they're just going to come apart like this. Now, what would happen if I remove the air from inside this cavity? Let's give it to Frank and find out what happens. So right now, Frank is hooking up our two plates to his vacuum pump and removing the air. All right, now let me try pulling it apart. It's actually really hard to pull apart. In fact, it would take a force of around 200 pounds to pull these two plates apart. That's the power of a vacuum. So now, when I release this vacuum, watch closely what happens. So I'm going to turn this valve. When I turned this valve, the atmospheric pressure came back into our chamber and it released our two plates. Thank you.
So each of one of those was a demonstration of removing atmospheric pressure from one side of the object and leaving it on the other side. Now you have a difference, right? And then you see these interesting effects. So what we're going to do now is, instead of removing atmospheric pressure from one side of an object, we're going to add extra pressure to one side. And we're going to use a T-shirt cannon for that. So I've got a T-shirt in here, and we've got atmospheric pressure pushing on one side, and I'm going to pump up the other side to about 2 times atmospheric pressure. Can't see it. There we go. You know how to release it. Just push through this thing right here.
Don't point it at your face.
All right, who wants a free T-shirt?
I've got another T-shirt.
Pick me direction, man.
What do you say, Frank? 3 times atmospheric pressure?
3 times, unless I get tired.
I'm pretty tired, Frank. We've been up since 6 in the morning.
We usually use an air compressor for this, but it didn't fit in my car.
You could lie and say it's 3.
Close enough. Okay, Brian.
Who wants another free T-shirt? I'll be right this time.
I've got one more T-shirt.
But his arms are tired.
We'll see how far we make it. You know what I need? A physics student to do this for me.
That's what you said about the bed of nails. It's Superman!
10 more, 9 more, 8 more, 7 more, 6 more, 5 more, 3 more, 2 more, 1 more, 2 more. Good enough.
Okay. Who wants the last free T-shirt? All right.
If you didn't get a t-shirt, have no fear. We've got them for sale after the show. And we wanted to show you what we do with the money we bring in from t-shirt sales, from donations, from ticket sales. We think we're doing a lot of good things for physics education in Northern California, but by far the biggest and best thing we do is bring in local schools from low economic areas to Foothill College to see the physics show. The physics show has grown quite a bit. This year we did 23 shows. Over 20,000 people saw the physics show at Foothill College this year. And because we only charge $5, but because we have so many people coming, we have some real money to do some good things with. This is one day we're bringing kids in to see the physics show. We pay for the buses. We put on the physics show. The kids get a tour of our beautiful college campus. They eat their lunch on campus. They even get a t-shirt. And as my friend always says, David always says, they leave with a t-shirt with the name of a college on it, and that t-shirt has nothing to do with sports. This is just one day. We did 5 days just like it this year. Next year we're doing 6 days like it. Over 5,000 kids are going to see the physics show next year. Thank you for helping us with that. Appreciate it. David, we started talking about pressure, but we never defined what pressure is. We never told them what pressure is. Pressure is a force per unit area. A force per unit area. What does that mean? It means if you're running around the house and you happen to bump into the side of the table, yeah, not so bad, right? But if you bump into the corner of the table, ow, right? The same force concentrated on a small area, very different effect, right? If David pushes on me with his open palm, not so bad. If he pushes on me with the tip of a needle, ow, right? The same force concentrated on a small area. Maybe you've seen somebody chopping vegetables in the kitchen. If the knife is nice and sharp, the force is concentrated on a small area, it goes right through the food, right? But if that knife is dull, that same force spread out over a bigger area doesn't have the same effect on the food. Pressure. So we're going to do a little demonstration with two of our favorite things.
Balloons!
And nails.
Best friends forever. So we're going to start off and we're going to try and balance this balloon on just 2 nails. Okay, now Frank is going to put on a weight. That was bad news for the balloon. Now we're scientists, we like to repeat experiments, but we're going to make a slight change. We're going to put this balloon on about 20 nails. Now I know what you're thinking. More nails means more holes, means it's going to pop even faster, right? No. Well, let's find out. 1 weight, 2 weights, 3 weights, 4 weights, 5 weights, 6 weights. We're all done waiting. Hey, wait a minute, Frank. Did you bring your indestructible balloon to the physics show tonight?
Sometimes I'm sneaky.
Is there any way we could figure out whether this is really an indestructible balloon? Yes. What? How? Put it on the 2 nails. Frank, we've got a sharp crowd tonight. Indestructible. Ah! Not indestructible.
It appears the number of nails makes a difference. Put a balloon on 2 nails, bad news for the balloon. Put it on a whole row of nails, not so bad. If we had a balloon on these 2 nails and we put 20 pounds of weight on top, each nail would have to push up with a force of 10 pounds to hold up its share of the weight. But if we have 20 nails and we put 20 pounds of weight on top, each one only has to push with the force of 1 pound to hold up its share of the weight. The more nails there are, the less each one has to push to hold up its share.
So Frank, let me see if I've got this right. If I put a balloon on 2 nails?
Bad news for the balloon.
But if I put a balloon on 20 nails?
Yeah, not so bad.
Frank, does this work for things that aren't balloons?
It does, even physics instructors.
Oh, Frank, if I put a physics instructor on 2 nails?
Ooh, bad news for the physics instructor.
But what if I put a physics instructor on a whole bed of nails?
Let's see what happens.
This is different with no music. Good. Other side. That's not right. Okay. One more. Good. Now. Okay. I need to put on my safety glasses because we don't want anybody to get hurt here. You can see what we're doing here, right? It's got a bed of nails underneath him, a bed of nails on top of him. We've carefully balanced a cinder block. Now I've got a sledgehammer. Frank, are you okay?
No leaks.
No leaks, he's good. Now, there are a lot of things keeping Frank safe during that demonstration. It's not just top quality safety equipment. The first thing I think about is that Frank is kind of like a really big balloon. If we put him on 2 nails, it would be bad news for Frank. But we put Frank on about 800 nails. And each one of those nails only has to push up with a little bit of force to support the forces that are in this problem. The second thing I think about is something called inertia. And that means if something is at rest, it wants to stay at rest. Now, the top cinder block and the top bed of nails, they all had inertia. So even though the sledgehammer wanted to make them move, they wanted to stay exactly where they were at. That protected Frank. And then finally, even though the sledgehammer has energy, it takes energy to bust up the cinder block. So when the cinder block shatters, that's also physics protecting Frank. So there's a lot of really great physics in that demonstration, and it's just a fun way for us to end our show.
So today we talked about temperature, sound, and pressure. Those are all topics under physics. Physics is part of science. Did you have fun?
Woohoo!
Foothill physics instructor David Marasco. Our student Brian Manuela. I'm Frank Cascarano. Thank you for coming. If you're interested in a t-shirt, come on up to the stage. Thank you. Woo-hoo.